Good morning, students. In the last class, we discussed about the derivation, that is the fringe width beta is equals to lambda d divided by b. So in that case, we are studying that the fringes we obtained is that are the point sources S1 and S2. In the Young's experiment, he considered the slits that are made by that is the screen. Here he made two pinholes, that is of the small holes. So for this we get the interference patterns, that is alternate dark and bright fringes, that is bands. Alternate dark and bright bands we are getting on the screen. So here he using two pinholes, that is the holes are very small. If we replace these two holes by the slits, then we get, so that is two slits replacing point source into slits, that is small gap. So these are the two slits. Before here one more slit he placed in the similar experiment. So this one is the single slit, and here we are using the double slit. So the waves, the sources which are coming and falls onto the single slit, from here the wavefronts are moving and falls onto the two slits, that is for the two sources. So these two slits acts as the two sources, then it is the double slits. So here also we are getting the interference pattern with intensities are more compared to that of the point sources. So here we get the interference pattern in the similar manner, that is in the straight lines, that is alternating bright and dark bands we are getting like this. So these are the fringes which we get through the slits. So if we replace the slits by, that is we replacing the point sources by the slits, then we get the fringes with the high intensity. So if we replace the point source by the slits, then we get the high intensity with the similar patterns alternating bright and dark fringes we are obtaining on the screen. So this experiment is called as Young's double slit experiment. So here he used the two slits, hence the experiment name called as double slit experiment. In the last class we studied that in the second screen we are using two pinholes, that is small holes from that spherical wavefronts are coming. So here in the slits we get the plane wavefronts, and here on the screen we get the bands, alternative dark and bright bands of high intensity. So the experiment name called as Young's double slit experiment. So if we plot the graph of intensity to the path length, so that is the intensity I is equals to 4 I naught, that is for the maximum intensity, and I is equals to 0, that is for the low intensity. For the high intensity, the bands which are in bright in color, and for the low intensity, the bands are in dark color. So this one is the path length or path difference. So here I will write path difference along x-axis and intensity along y-axis. Then we get the curves. So here also. So this one is the graph for intensity versus path difference. So intensity along y-axis and path difference along x-axis. Then here we get this one is the maximum intensity, that is I maximum, that is equals to 4 I naught, right? So this is for at 0, because at 0 we have the part difference is same. S1P is equals to S2P, that is at the center. Then we get the maximum intensity for I naught. So next maximum intensity is here. So this one is at the maximum intensity. Then here we get lambda. So next maximum intensity is here. Then here we have 2 lambda. Next here it is 3 lambda. Similarly, if we write here it is lambda, that is 1 lambda, 2 lambda, 3 lambda, and here it is 2 lambda. So at here we have the minimum intensity, that is 0, 0 and 0. So here the intensity is minimum and here the intensity is maximum. So it is 1 by lambda, then it is 1 by 2 lambda, half lambda, that is odd integers, that is 1 by 2, we get the intensity is minimum, and if it is lambda, then we get the intensity is maximum. So that is S2P difference of S1P, we write n into lambda. So this gives constructive interference, that is for the bright bands we get the maximum intensity for n values is 0, 1, 2, 3 like this. So if we substitute 0 here we get the maximum intensity. If we substitute 1, that is 1 lambda, we get the maximum intensity. If we substitute 2 lambda, then we get the maximum intensity 2 lambda. So the same S2P difference of S1P n plus 1 by 2 into lambda. Here also the values of n is same, that is 0, 1, 2, 3 and so on. So if we substitute here 0, then we get 1 by 2 lambda. So here is the 1 by 2 lambda. Then here the intensity is minimum, that is I is equals to 0. This is for the destructive interference. Here the band is dark in color, that is I is equals to 0. For n is equals to 0, here we get 1 by 2 lambda. Next if we substitute 1, then it is 3 by 2 lambda, that is here. There also we get the intensity 0. Similarly here, then also we get the intensity I is equals to 0. So this is the graph for the intensity to the path difference, right? So we will solve few problems on this topic. Almost every year they ask the problem on this topic only, that is fringe width. Beta is equals to lambda d divided by d. So from last several years they asked 5 marks problems on this topic only. So you have to, that is based on the formula fringe width beta is equals to lambda d divided by d. Here we have two d's. So one is capital D and another one is small d. So capital D represents what? The distance between the slit and to the screen. So here we have, this one is the slit, secondary slit, and this one is the screen means. So this distance is what? That is small d, right? Next here is the capital D, the distance between the slit and the screen, and here is the distance between the two slits or between the 2-point holes. So that one is D, and lambda is the wavelength of the light used here. So from here it is coming means the lambda is the wavelength of the light used by the source. So here beta is the fringe width, that is the width of the fringe, that one we call as fringe width. So in the problems they given, here we have 4 parameters, beta, lambda, d and d. In this they given either 3 parameters, we have to calculate 1. If they given beta, lambda, d, then we have to find the distance between the slit and the screen. Otherwise if they given d and we have to calculate the distance between the slits, or they given lambda, d and d, we have to find the fringe width beta. So let's solve the problems. In that first problem, is a monochromatic monochromatic light of wavelength. Light of wavelength 5000 angstrom, 5000 angstrom from a narrow slit, from a narrow slit is incident on the double slit if the separation of 10 fringes on the screen one meter away is 2 centimeter. Find the slit separation. Find the slit separation. So in this question they given a monochromatic light of wavelength 5000 angstrom. So here the light we are using is 5000 angstrom, and from a narrow slit is incident on the double slit if the separation of 10 fringes on the screen 1 meter away is 2 centimeter. Then find the slit separation. So here they given first, if we write what they have given. So first they given the wavelength, that is 5000 angstrom. So if we convert into the meters, then 5000 into 10 to the power of minus 10 meter. That is 1 angstrom is equals to 10 power minus 10 meter. Next, the separation, if the separation of the 10 fringes on the screen 1 meter away is 2 centimeter. That is the distance between the slit and the screen is 1 meter. That is they given capital D is equals to 1 meter. And also they given the separation of 10 fringes on the screen is 2 centimeter. That is, if we consider this one is the screen, in the last derivation we consider one point. If we observe here, from here to that point we have how much fringes? That is 10 fringes, and its length is 2 centimeter. So here we have 10 bands and its distance is 2 centimeter. That is, x distance is 2 centimeter. We have to calculate, from that we have to calculate the beta, that is the single fringe width. And here finally we have to find the slit separation. That is slit separation nothing but small d. So we have to calculate small d how much. So we know the formula, fringe width beta is equals to lambda d divided by d. So here we are going to find out small d. They given lambda and also d, but we have to find out beta by using this one. That is 10 fringes on the screen is 2 centimeter. That is 10 fringes, that is 10 beta. So fringe width, one fringe width is beta, then they given 10 fringes, that is 10 beta, that is equals to how much? The distance it is 2 centimeter, right? Then beta is equals to 2 into 10 to the power of minus 2 centimeter, converting into the meter, then divided by 10. Beta is equals to 2 into 10 to the power of minus 3, right? So it is meter. Beta is equals to 2 into 10 to the power of minus 3. Now substitute here, we get d. So if we replace d is equals to lambda d divided by beta. So we know the value of lambda. So the value of lambda is 5000 into 10 to the power of minus 10 into 1 divided by the value of beta is 2 into 10 to the power of minus 3. So it becomes, if it shifts to the numerator here, we can write 5 into 10 to the power of plus 3, right? So simplification, 5 into 10 to the power of 3 into 10 to the power of minus 10. So minus 3, if we shift to the numerator, it becomes plus 3. 10 to the power of 3 into 1 is into 10 to the power of 3. So remaining is 5 divided by 2. So the final answer is, sorry, we write here on 5 divided by 2 is 2.5 into, so 3 plus 3, 6, minus 10, that is minus 4, 10 to the power of minus 4. So if we shift one more, that is divided by 10, then it is 0.25 into 10 to the power of minus 3 meter, or we can write D is equals to, so that one final answer 0.25 millimeter. So either we can stop here, that is 0.25 into 10 to the power minus 3 meter, or we can write it as D is equals to 0.25 millimeter. So in this question they are not directly given the beta value, that is they given for 10 fringes, the separation from here to here is 2 centimeter. That is from, this one is the center, from O to P it is 2 centimeter. In this 2 centimeter we have 10 fringes, that is we have 10 bands. So each band's length is how much? Beta, that is fringe width. So 10 into beta is equals to 2 centimeter. Then we get each fringe width value is 2 into 10 to the power of minus 3 meter. Now substituting the values of lambda, d and beta, we get the small d, that is distance between the slits, that is equals to 0.25 millimeter, right? Next. So in this question you have to remember this one. So next, second question. In Young's double slit experiment, distance between the slits is 1 millimeter. The fringe width is found to be the fringe width is found to be 0.6 nanometer when the screen is moved through a distance of 0.25 meter. The fringe width becomes the fringe width becomes 0.75 nanometer. Then calculate the wavelength of light used. Right? So here in the Young's double slit experiment, distance between the slit is 1 millimeter. The fringe width is found to be 0.6 nanometer. When the screen is moved to a distance of 0.25 meter, the fringe width becomes 0.75 nanometer. Calculate the wavelength of the light used. So here they given the two conditions. So in the first condition, what they given is the slits, that is, so what they given is the distance between the slits, that is they given small d is equals to 1 millimeter, that is equals to 1 into 10 to the power of minus 3 meter. Next, for this, the width is found to be 0.6 nanometer. So they didn't give the distance between the slit and the screen, that is we taken d as d, that is d itself. Next, the fringe width is found to be 0.6 nanometer, that is they given beta is equals to 0.6 nanometer, that can be converted into the meter, means 0.6 into 10 to the power of minus 9 meter. Nano means 10 to the power of minus 9, right? So next, what they say is when the screen is moved through a distance of 0.25 meter, the fringe width becomes. So here, so this one is the slit, and here is the screen. So here for the first case, it is d, and distance between the slits the given is small d is equals to 1 millimeter, right? For this they given the fringe width which appears on the screen is 0.6 into 10 to the power of minus 9 meter, that is 0.6 nanometer. So in the second case, what they are saying, when the screen is moved through a distance of 0.25. So if this screen is further moved, for the second case, so this screen is moved by a distance of how much they given? 0.25 meter. So when the distance is moved away, then the fringe width becomes. So for the second case, we can write this distance is same, that is d as is d is equals to 1 millimeter, that is equals to 10 to the power of minus 3 meter. So next, capital D, that is distance between the slit and the screen. Now observe here the distance between the slit and the screen is d plus 0.25 meter, that is d is equals to d plus 0.25, it is in meter. Next they given the fringe width becomes, that is beta, beta is equals to 0.75 nanometer, that is equals to 0.75 into 10 to the power of minus 9 meter. So here if we consider this one first case, then here the second case we can write it is d dash beta dash. So d remains constant. Either we can write here it is d1 beta 1, here we can write d2 beta 2. So from this we have to calculate, that is we have to find the wavelength of the light used here. By using these two conditions, we are going to find out the lambda. So we know the fringe width beta is equals to lambda d divided by d. So if we write for the first case, we have beta is equals to lambda d divided by d. So if we write for the second case, that is beta dash is equals to lambda, here b is unknown, that is in both the cases we are using the same source, then the lambda is same for the both the cases, then lambda d dash divided by small d. So here d dash represents what? That is increasing in the length. Here small d, it is constant. So if we substitute the value lambda, so d dash can be written as, from here d dash can be written as d plus 0.25 divided by d. So if we further simplify, we get lambda d divided by d plus 0.25 lambda divided by d. So from here, by observe here, we get substituting the value of lambda d divided by d, we can substitute that value into beta. So if we write, it becomes beta dash is equals to, here this value can be written as beta, that is equals to, sorry, beta plus, this one is as is 0.25 lambda divided by small d, right? So now we know beta dash value, and here we know beta value. Then substituting it here we get, or if we shift it to the LHS, then becomes 0.25 lambda divided by d, that is equals to beta dash minus beta, right? So we need lambda, then lambda is equals to beta dash minus beta into d divided by 0.25. So now substituting the values of beta dash, beta, d, then we get the wavelength of the lambda, right? So now I will substitute here, that is lambda, that is equals to beta dash minus beta into d divided by 0.25. So beta dash value is 0.6 into 10 to the power of minus 9 minus, sorry, this one is beta dash is 0.75. So 0.75 into 10 to the power of minus 9 minus beta value is 0.6 into 10 to the power of minus 9 into d value is how much, 10 to the power of minus 3 divided by 0.25, right? So next 0.75 minus 0.6, that is 0.15 into 10 to the power of minus 9 into 10 to the power of minus 3 divided by 0.25. So if we simplify, it becomes 15 by 25. If we shift the zeros, then we get 15 divided by 25. So right. So 15 divided by 25. So 5 3 is 5, 5 is that is 3 divided by 5, that is we can write 0.6. So 15 divided by 25 can written as 0.6. Here 10 to the power of minus 9, and here it is 10 to the power of minus 3. So we get into 10 to the power of minus 12 meter. So 0.6 into 10 to the power of minus 12 meter, or we can write lambda is equals to. So if we multiply 1 0, it becomes 11, another 0 if multiply it becomes 10, then we can write, if we multiply, then here we get 600 nanometer, right? So this one is the final answer. The wavelength of the light used here is 600 nanometer, or we can write 6000 angstrom, right? So this is the simplification. So here they given the two conditions, that is initially we have the screen D, then they moved further the screen by 0.25 meter, then we know the formula of fringe width beta is equals to lambda d divided by d, then we substitute and simplify, we get the answer 6000 nanometer. Next problem, that is third problem. In Young's double slit experiment, while using a source of wavelength 6000 angstrom, the fringe width is 5 nanometer. If the distance between if the distance between the screen and the plane of the slits is reduced to half, what should be the wavelength of light to get fringe width to get fringe width 4 millimeter. So here in the question the given in Young's double slit experiment while using a source of wavelength 6000 angstrom, the fringe width is 5 nanometer. If the distance between the screen and the plane of the slits is reduced to half, then what should be the wavelength of the light to get the fringe width of 4 millimeter? So here also we have the given two cases. So in these two cases, in the first case they given the wavelength. So in the first case, they given wavelength of the light, that is lambda 1, that is equals to 6000 angstrom, that is 6000 into 10 to the power of minus 10 meter. Then for that the fringe width is 5 nanometer, that is they given beta 1 is equals to 5 nanometer, that is equals to 5 into 10 to the power of minus 9 meter. If the distance between the screen and the plane of the slits is reduced to half, so here also they didn't mention the distance between the screen and to the top of the slit. That is, we are considering D1 as D. So here we have two cases, that's why D1 is equals to D. Next, in the second case, what he is saying that, so in the second case, the distance between the screen and the plane of the slits is reduced to half. That is, the distance is reduced to half. D2 is equals to D by 2. Initially it is D, then it is reduced to D by 2. So what should be the wavelength of the light? That is, we have to calculate the wavelength of the light lambda 2 to get the fringe width of. So in this case they given the fringe width of beta is equals to, that is beta 2 is equals to 4 millimeter, that is 4 into 10 to the power of minus 3 meter, right? So this is the given question. They given two sets, that is one is lambda 1 beta 1 d1 and d2 beta 2, we have to find the lambda 2. So in these two cases the common is the distance between the slits, that is small d. So from the first case we are going to find out the small d, then that small d is constant for both the cases, then we substitute that d to the second case, then we get the wavelength of the light, that is lambda 2. So in the first case, we know the fringe width beta 1 is equals to lambda 1 d 1 divided by d. So here in the first case we know beta 1, lambda 1 and d1, that is d1 we have taken in terms of d. So we have to find small d. Then small d is equals to lambda 1 d1 divided by beta 1. So the wavelength lambda 1 is 6000 into 10 to the power of minus 10 into d1 is taken as d beta 1 5 nanometer, that is 5 into 10 to the power of minus 9. So next here 5 12 are 60. So 120 d into 10 to the power of minus 10. If we shift minus 9 to the numerator, it becomes plus 9 minus 10 plus 9, that is minus 1, that is we get 12 d. So small d is equals to 12 d, right? Thousand 200, that is 120 d. Small d is equals to 120 d. 5 ones are 5, 5 twos are 10, 1200 d into minus 10 plus 9, we get 10 to the power of minus 1. If we divide it by 10, we get 120 d. So now substitute for the second case, that is beta 2 is equals to lambda 2 d2 divided by d. So here we are going to find out the lambda 2. That's why lambda 2 is equals to beta 2 d divided by d2. So this goes to the numerator and d2 comes to the denominator. Now, so we know the value of beta 2, that is 4 millimeter. 4 into 10 to the power of minus 3, and small d value, that is 120 capital D, that is 120 d. So here d2 is how much? That is half. That is here reduced to half, that is it becomes d by 2. So in the numerator d, denominator d get cancelled, then it 2 goes to the numerator, then 4 into 2 into 120 into 10 to the power of minus 3. So that is 4 2s are 8, 8 2s are 16, right? So 8 plus 8, 960 into 10 to the power of minus 3, that is meter. So the wavelength of the light when the fringe width is 4 millimeter. So we get the wavelength of the light used. So right. So this is another type of the problem. Here also they given the two cases. In the two cases, the small d is same. That is the slit width is same d. Then first we find out the value of d. Then substitute to the second case. We get 960 into 10 to the power of minus 3 meter. So take one question as homework, that is try at home. So this is for homework. In Young's double slit experiment, fringes of certain width are produced on the screen or kept at a certain distance from the slits when the screen is moved away from the slit by 0.1 meter, fringe width increases to fringe width increases to 6 into 10 to the power of minus 5 meter. Then separation between the slits is 1 millimeter. Calculate the wavelength of light used. So this is for the homework. Try this question. In the next class, we will continue few problems. Thank you.